Welcome to the lecture on design features for static and fatigue loading in welding. So, we had the introduction about the static loading cases and the fatigue loading cases. What are those considerations which are required to be understood when we talk about the static loading cases in welding, and while fatigue loading cases in welding. So, we must have the idea about those things, because that will help us to assess the failure of the component. And so as a welding metallurgist, when you have to do the failure analysis, in those cases you can have the use of these concepts as well. So, if you talk about the design features when we talk in the case of static loading. So, in those cases, as we have seen that we are designing based on the strength and rigidity. So, we are talking about the allowable stress values, and we are talking about the strains or stresses or so. So, we will talk about the standard formulas, some of the design formulas which are used when we when we talk about the design under these different types of loading in the case of static loading case. So, if you say take the tensile loading, now as we know, this is we must have the idea that when we have any member which is subjected to tension. So, we are a tensile force is applied, and that is applied in line with the center of gravity of the section, and then it will be giving you the unit tensile stress, and that will be P by A. So, that P is the tensile force which is applied to the member, and then A is the area of cross section right angles to the line of the force. So, that way we get these stress value, and that stress value should not anyway, that has to be less than the value at which it will fail. So, accordingly the design parameters are adjusted like that. So, then also if you talk about the value of the strain. So, as we see that strain will be the stress value which you get divided by the E. So, that is stress by strain becomes the E value, that is modulus of elasticity. So, accordingly you can have the value that is sigma I upon E. So, that way you can have the these values. And if you talk about the total elongation or displacement, then that will be when you talk the total elongation or displacement. So, that will be epsilon into L. So, that is your tensile strain. So, that is this into the length of the member. So, that way you are going to have the calculation of the dimensions or the parameters in case of tensile loading. Now, if you have the case of compressive loading. So, if you come to compressive loading, so basically the members will be subjected to crushing if the compressive strength is exceeded. The stress which is generated is more than that compressive strength of the material, but that is seldom that is very rarely that case comes under the compression case. So, mainly what we need to design in the case of compressive loading is the design against buckling, because depending upon the length of the member, you will have the slenderness effect that will be coming into picture. So, you will have to design against buckling. So, you will have columns if if the slenderness ratio is measured, you will have the slenderness. So, slenderness is basically measured as the ratio of unsupported length L to the least radius of gyration. That is R of the column. So, what happens that this slenderness ratio becomes important. So, when your slenderness ratio will be higher, so it will have more chances to buckle. So, this is they will so in those cases the column will start moving laterally, in that case rather than getting crushed, it will start moving laterally, and that will be also at a stress which will be lower than the yield strength of the material. So, a component which is here, it will try to buckle in the case of so what will happen. So, this axis will start buckling when your slenderness factor is coming into account, and for that you find these you will have the radius of gyration. So, the least radius of gyration is computed, and you will have a range to this value of L to R. So, that range has to be that range is basically specified, and if that range is that range of value is not satisfied, in that case you will have the buckling experienced in the case of these compressive loads. Then next is your bending. So, you will have the bending loading. Now, in the case of bending, you will have the theory of bending which is applied, and theory of bending tells that M by I will be same as E by R upon equal to sigma x by y. So, you will have the different terminologies, you will have different terms which have different meanings. M is the external bending moment at section. So, you will have a section which is considered, and and then you will have sigma x is the bending stress at perpendicular distance y from neutral surface. So, that way you get, and then R becomes the radius of curvature of the beam, and then you have rest is left is the E, that is your Young's modulus of elasticity. So, that is of the material. So, many a times we replace this sigma x, that is with the bending stress, basically Fb or F. So, in that case, if you replace this sigma x with the Fb, so your equation becomes M by I equal to Fb upon R, that will be sigma. So, that is E by R. So, you will have E upon R, that will be, so that will be Fb upon y. So, that way you will have, this is the bending or the flexural equation that is known as, and based on that you will be designing. Now, many a times we design for the y max in that equation, and you will have the M by Z as the I max. So, F max, that is because of the y max considerations, because Z becomes I upon y max. So, that is Z is the section modulus. So, if you take this section modulus as the parameter, you will have Z as the I upon y max. So, these parameters can be computed for the calculating these the required dimensions and solving the problem when it comes for the bending type of loading. Now, you may have also the considerations of strength and stiffness. Of beams. So, what we do is that strength is normally proportional to the section modulus. So, strength will be proportional to Z. That we had discussed in our earlier class, and stiffness is basically load by elongation. So, that is your rigidity is what so that is about the that is same thing which is represented by the Young's modulus. So, load by elongation. So, this will be proportional to EI. So, to satisfy this condition, the beams should be deep, for getting these shear and the strength and stiffness of the beam when we are talking about the welding and when we are designing for the static load conditions in bending. Then we have other loading conditions also. Now, you may have also the case of torsional loading. So, when you have the torsional loading, so torsional there are cases when these torsional resistance is required, and there will be torsion which is there. So, that will be creating in the design of bases and frames, that creates problem while we design for the bases and the frames. So, basically we have torsional resistance which is required to be found out. So, of flat section, it is found by the formula R, that is WT cube by 3. So, R is the torsional resistance. Then you have the W as the width of flat section, and T is the thickness of flat section. So, once you find the torsional resistance of open section, in that case you can have the calculation of the angular twist, because torsion creates the twist in the material. So, you can have the value of the angular twist. So, that will be T into L upon Es into R. So, this way you can have the calculation of the angular twist. So, you will have this value in radians, that is this is your angular twist, and you have other as we know, you have T as the torque, then you have Es as the modulus of elasticity in shear, and you have R as the torsional resistance. So, each part will of the section, basically open section will be twisting to the same angle as the whole member in this case. Now, the unit angular twist, that is equal to the total angular twist divided by the length L. So, your unit angular twist will be the total angular twist which you get theta, and that will be divided by the length. So, now for once you know this unit angular twist, so by dividing this theta with the L, so you can find the resulting shear stress on the surface. So, resulting shear stress on the surface tau, that will be phi times T into Es. So, that will be T into T upon R. So, basically here the T becomes the thickness of the section. So, you can have the shear stress which is being used, and accordingly you can have the value of these shear stresses and the unit angular twist and all that, total twist, then you have also. So, all these things can be computed by using these formulas, and then what you do is that for the different geometries you can have the different formulas for finding these torsional resistance, like if you have the torsional resistance for suppose a tubular shape. So, in that case you will have the values based on the the thickness or so. So, you can have the different formulas for finding that. If you have a popular sections, like if you have closed tubular sections. So, for a circular in the circular form it becomes 2 pi r cube multiplied by T. So, if the r is the suppose for this section, if you find if this is the r and this is T, in that case it becomes 2 pi r cube T. So, accordingly you can have the these values of the torsional resistance basically being computed, and the torsional resistance R. So, once you compute that, then for the different type of geometries you can have the calculation of other different parameters which is required to be calculated, that can be found out. So, this is normally these are the formulas which are used in the case of the static loading, and there we have talked about the different type of forces, the tensile, or you have the bending, or maybe the torsion. So, in those cases this is how you try to calculate these torsional resistance values. Now, if we talk about the fatigue loading cases, so as we had discussed that in the case of fatigue loading, if you try to determine the fatigue strength of the component of a particular material. So, in those cases we use the SN curve or the Euler line. So, what we do normally that in that case we try to test the several similar specimen you are testing under the given loading conditions, and then each of these specimen will be subjected to the given cyclic stress, and then the number of cycles which is up to which it is getting fail, that is recorded. So, in that case you have the the formation of you try to have these SN curves. Now, what we do is you will have the relation between the applied stress, that is your stress range. So, you will have the stress range in this case S max minus X min, and also you will have the failure. So, that will be the number of cycle to failure. So, that is basically known as the N. So, this data is basically plotted, and that that this is known as SN curve or the Euler line. So, that can be you can have a typical SN curve which shows this this kind of graph. So, you will have this is the stress value that is in Newton per mm square, and this is your number of cycles to failure. Now, in most of the cases, when you try to plot these these plots on the log scale, in that case it becomes a straight line. So, what we do is that if you try to plot the log plot, so it will be log scale here also, and this is also and that is in log scale. So, in those cases this comes as a straight line. So, what will be happening that in these cases you can have the once you have the log scale. So, accordingly you will have the equations which will be representing these lines. So, that will be represented by the equation like F2 equal to F1 into N1 by N2 raised to the power k. So, suppose for the stress value F1, if the number of cycles up to which it sustains is N1, and for N2 it will be F2. So, in that case you will have this sloping line that can be expressed in terms of this value. So, this line will be F2 equal to F1 into N1 by N2 raised to the power k. So, that way you will have this equation. So, F1 is the fatigue strength compared to as for the N1 number of cycles, and F2 is for the N2 number of cycles. F2 is the stress that is S max minus S min. So, that will be your for the for that failing in the N2 number of cycles. Now, this constant k will be varying, and the k value is normally you will have the k value is normally close to 0.13, whereas its value is about 0.18 when we use the axial loading. So, tension or compression. So, in those cases it may go maybe up to the value of 0.18. Now, there are only one type of stress that is shown. Now, there may be typical stress cycles which are used in these fatigue tests. So, you will have the typical type of these stress cycles which we use, and these cycles are basically you will have the stress cycles like if you have this way, this is the cycle. So, you have only tension. So, this is basically the tension, and here in this you can take the tension on this side, and you will have that is a stress. So, this is your S max. Then if you take the so this is basically the pulsating tension type of test. Similarly, you may have the stress cycle that may be evenly on the up and lower side. So, basically this is the example of alternating type of stress. So, this will be your S max and this will be your S min. Now, what we mean to say that you get the difference between the S max and the S min. So, that is how so S max is you have the positive value, and S min you have the negative value. So, here it is compression, and this is your tension. So, this is your stress value, either compressive or tensile. So, this is known as the alternative type of cycle. Then you may have also the cycles. It may be you have some value, that is S min is this is S min, and you have from here it is starting. So basically it goes like that. This is your S max. So S min is basically half of S max. So this is known as in this case you have only tension. So the stress is only tensile, and this is known as the half tensile. So you have the different type of stress cycles which you can see in these cases, and you have 0 to tension, and then you have to complete reversal also. So these are the different cases which is formed here. In these cases you have 0 tension here, and then in this case you have the half tensile. So based on that basically you have a diagram which is also formed, and that is known as the Goodman diagram, and it will be talking about the effect of the various type of stress cycle on the fatigue life. So depending upon the different type of cycle, what will be your fatigue life. So that will be it will be talking about that, and that is represented by a Goodman diagram. Now if you talk about the fatigue life of the non-ferrous materials. So non-ferrous materials they also behave, they have they also exhibit the fatigue limit. So if you try to draw the for the fatigue limit for the non-ferrous materials, so it goes like this. So if suppose if you find for the steel, it goes like that, it goes like this. But for the non-ferrous materials it will be going like that. So this is your log n, that is your fatigue life, and this is your stress. So what you see, this is for the steel, and this is for the non-ferrous materials. So they basically change, and there is difference between the the way they respond to the fatigue loading for the ferrous and the non-ferrous materials. So normally you have a fatigue limit which is defined. Now normally commonly what we do, normally we have a procedure when we talk about the calculation of the fatigue life. Then what we do is we try to have the definition of certain parameters. So normally we are comparing the we are normally partially comparing the materials, and we plot the partial unnotched fully reversed condition, that is SF. So we have the SF, that is that is the when we are doing the in case of completely unnotched condition, and we are doing the complete reversed conditions. So SF is the unnotched fully reversed fatigue limit. So that is your SF, and then that we compare with the ultimate tensile strength. So your SU is the ultimate tensile strength. So and then we take its ratio, so SF upon SU. So this SF upon SU, it is known as the fatigue ratio. Now most of the data which is found, suppose for any material you can have the data for the SF and also for SU, and when you calculate these ratio, this ratio is known as the fatigue ratio. Now in most of the cases this varies between 0.2 to 0.65. So, normally the SF will be a general tendency is that the SF will be increasing linearly with SU, but that is not normally true, not very much true many times. And what has also been some generalized equations are there, like SF will be 0.5 SU when your SU is less than 1400 megapascal, and SF will be 700 megapascal for SU is more than 1400 megapascal. So, these are the relationships which by which you can have the calculation of SF. Now, many a times we try to increase the fatigue limit of also the component, and that can be done and we can check it against these findings. Now, in general, what is it is found that the stress, that is your SM, that is your so in these cases that is when we talk about the mean stress. So, in the case of the fluctuating stress, you have the one value is the mean value. So, this is detrimental when it is tensile and beneficial when it is compressive. So, that is in normal case it has been found that if your SM is tensile, then it is detrimental, and if it is compressive, then it will be somewhat beneficial. So, that basically so what happens that you will have that can be found out by looking at the values. Suppose you have the alternating stresses, and if it is n. So, what has been seen that if your curve will be something, it will go like this. So, this will be the SM when it is in compressive mode, and this is SM when it is tension. So, if the mean stress is in compression, then you will have the more fatigue life that is found. Now, the effect of the tensile mean stresses on the for different materials and situations are given by the different types of equations. So, the modified Goodman equation, so that basically tells about these different conditions, like you have SA upon SF plus SM upon SU, that will be 1. So, similarly you will have the Soderberg equation. So, these equations they tell that SA by SF plus SM by SY, that becomes 1. Similarly, you have the Garber equation. So, this Garber equation is SA upon SF plus SM upon SU raised to the power 2, that is 1. So, this way you have these relationships by which you can measure. So, in these cases you have SA is basically SR upon 2. So, your that is your S max minus S min by 2. It is range, so that is your S max minus S min by 2, and then SM is basically the mean value. So, this will be S max plus S min by 2. And then if you talk about the SY, so SY is the tensile yield strength of the material, tensile yield strength of material. So, these equations are used for the while we calculate these while we do the analysis in fatigue loading. So, so what we see from here, that if you have a completely reversed bending that is occurring, in that case your SM will be 0. So, that is S max plus S min by 2. So, you will have, if it is completely reversed, in that case that becomes 0, and so your SA becomes SF, that is your fatigue endurance limit. So, that is so this way we try to have the analysis when we talk about the fatigue loading cases, and we can correlate them. We can have the other way also, the checks, you can have the study of other aspects also in the case of failure. But then we must be conversant with these terminologies, because that will help us in analyzing these situations when we have to deal with the failure of the materials, and we have to correlate it with metallurgically investigations. So, in those cases these understandings will help us to know that. So, dear students, this is the final lecture, and I hope that you have enjoyed this series of lectures for this course, and I hope that you will enjoy it. You will continue to enhance your learning levels by referring to the standard textbooks and reading more and more, and hope for a good exam so that you can pass with a very good marks and all that. Thank you very much.